Hi guys. So today we're going to look at a specific exponential function, and this is going to be with the base of e. Now e is actually a constant. That letter is actually going to stand for a certain number. That number is referred to as Euler's number. Okay, there's a couple different ways that you can estimate it. One of the most common ones is using this formula here. Now, it's not just plugging in any number. As you plug in larger numbers for x, this number is going to get closer to the actual value of e. So if you were to plug in 1 million, it's going to be a lot closer than if you plug in the number 10. Okay, so the largest number you could plug in is going to give you the closest answer for e. So what we're going to do just to show that is we're going to plug in a couple values here. So if I start by plugging in 10, then I'm going to see what I get for that value, and that is going to be 2.5937. So if I plug in a larger number like 100, that would be 2.7048. If I plug in a larger number, 2.7169. Okay, another number, 2.7181. Then I'm at 2.7183. Then I'm at 2.71828. So as I add in larger numbers, what you'll notice, again, the 2.718 kept being consistent there because we're getting closer and closer to the value, and what was changing were those later decimals. So what we're going to say, it's approximately 2.718 for what we deal with in here. Now there is another way that you can estimate it using this formula with all the exclamation points. If you continue to follow this pattern, you continue to add these things together, you'll also get a very good estimation for e. What these exclamation points are is something called a factorial. Now we're not going to use them a lot in this class, but you'll see these in future math classes. What a factorial is, it means you take that number and you multiply it by every whole number that follows. So 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial would be 5, 4, 3, 2, 1. Now, 0 factorial is actually 1. We don't really have time in this class to get through the reason why for that, but that's what you would do if you were to actually evaluate e this way. All right, so again, e is an irrational number, very similar to pi. That means there is no perfect fraction that can define it. We're going to estimate it to about 2.718. Another very unique thing about the function e to the x, what's going to make this function very important when you get to calculus that's really unique about it, the slope at any point on the graph, so like here's our e to the x function, okay, the slope, if I were to like just find what the slope was at a certain point, the value of that slope is going to be the same as the y-coordinate at that point. And again, we're not going to look at that in this class, but that will be really important later on, and that's why this function becomes really important in calculus, and that's why we're learning about it now. All right, so we're going to start just with reviewing some exponent rules. So e to the third times e to the seventh. Because they have the same base, I can add the exponents. But what we have to remember here, even though I am adding these exponents together, this is not a variable raised to the 10th power. E to the 10th power actually is a number, okay? It actually stands for a value. It is 2.718 to the 10th power. In fact, I can go ahead and give you the actual decimal here. This is 22,026.47. Okay, so just keep that in mind that even though we can follow those same rules, e is not a variable, it actually is a number, but this is the most simplified way to write it. All right, same thing here, exponent rules on b. 25 divided by 5, we would just divide. When I'm dividing same base with the exponents, I subtract. So 13 minus 12, so I just have 5e. And then again, power to a power, you would multiply the exponent. Everything would also get that exponent. So 2 to the 5th, e to the negative 15x. So this becomes 32. Since it's a negative exponent, e to the 15x moves to the bottom. All right, now, when it comes to growth and decay, we specifically looked last class at bases when our base was greater than 1 or when our base was between 0 and 1. Now, if e is our base, obviously e is greater than 1. So there's a different way to show growth and decay with e instead of just looking at the base. What instead we can look at is whatever we have next to the x. Okay, so that r If that is a positive number, then it's going to show growth, whereas if it's a negative number, it's going to show decay. So e to the x is going to look like our normal function, but e to the negative x, that would show decay. So that negative exponent on a number greater than 1 for a base will also show decay. All right, so let's look at these examples. So 3 times e to the x, because that is a positive exponent, this would show growth. Okay, and just to list a couple points that are going to be on here, we know there's still that asymptote at y equals 0. That has not changed. 0, 3 is still my initial amount because that is my a value. Okay, again, if I plugged in 0, e to the 0 is 1, 1 times 3 is 3. All right, if I plug in 1, then I would have 3 times e. So I would have 2.718 times e. Now, that you could probably go ahead and use a calculator for if you wanted to actually find what that was. So it'd be about 8.15. Okay. And then 4 to the negative, or 4e to the negative x, that is going to show decay. Okay, because again, negative exponent is going to make our graph go in the opposite direction. So again, this graph is still going to go through 0, 4. That's still my initial amount. Okay, but again, this time it's showing decay. So if I were to plug in -1, okay, that would give me 4 times e, which would be, again, 2.718 times e, which would be 10.87. So again, the negative value gives me the higher value, so that helps you see which direction it's going. All right, so again, positive exponent is going to show us growth. Negative exponent is going to show us decay when our base is e. Okay, because again, that base is still greater than 1. All right, again, very similar to what we did last class, just trying to rewrite these into this growth and decay form. So e to the negative 0.5 times x, that is e to the negative 0.5 times x. So e to the negative 0.5, I can evaluate that. So e to the negative 0.5 would be 0.6, whoops. That would be 0.6065 to the x. So then again, I would rewrite that, since this is decay, into 1 minus 0.3935 to the x, which makes it easy to see our percent change. And our percent change, this would be a 39.35% decay. Again, we know it's going to be decay because we have a negative exponent. All right. Again, let's look at b. Okay. So 0.5 does not get multiplied or by e to the 0.8, or sorry, it gets multiplied by, it does not get raised to that exponent. Okay. It's very important that that 0.5 stays over here. Okay. That 0.5 does not have an exponent. That is your a value. It has to stay separate. So all I'm going to evaluate is e to the 0.8, which gives me 2.2255 to the x. All right, so again, that 0.5 stays separate. So this is 1 plus 1.2255. So I can see that my, all right, so again, 0.5 would be my initial amount. My percentage would be 122.55%, which is a large growth. And again, we know it's growth because our value up there is greater than 1. Right. So next thing we're looking at is domain and range, and we're going to look at this from transformations. Now, we're going to spend a lot more time on transformations later on in this unit, but I want you guys to just start to see these because you are pretty familiar with these from other units. So e to the x plus 1, because that plus 1 is next to the x, I'm going to go to the left. Okay, this would be a horizontal change. Now, think about what this normal function looks like. Okay, if I shift that to the left, it is not going to change my range. And my domain for every exponential function is going to be negative infinity to infinity. No matter where I shift or stretch it, that is still going to be my domain. And my range has not changed from my original parent function. Okay, looking at b, again, knowing what we know, away from the x is vertical. So this is going to be a vertical stretch by 3 and down 5. So that's not going to affect our domain. Okay, but it is going to affect our range, okay? The stretch is not going to affect our range, but shifting it down 5. Again, if I take this graph and I stretch it, okay, it's not going to change our domain. What changes our range is actually when we move that down. So our range now is going to be from -5 to infinity. All right, now this last one, again, the only change here, it's gone up 1, which again will not affect domain, but that will affect our range, and our range is going to be from 1 to infinity. All right, the last thing we're going to look at is a really important application. So we started compound interest last class, but this is a different type of compound interest. So we looked at interest that's compounded daily, weekly, monthly, however often, but this type of interest is if it's compounded continuously. So if you look back to that formula that we looked at for E, it actually looked pretty similar to your compound interest formula. So if you kind of consider those two things together, E is a good base for us to use when interest is compounded continuously. So if our interest is compounded continuously, we're going to use this PE to the RT formula. P is still principal, R is still our rate as a decimal, T is still time in years. Okay, but E is just the Euler's number E. So if you have $5,000 to invest in an account that earns 1.75% annual interest, compounded continuously, that's how we know to use this formula. How much money will you have in 10 years? So I would take 5,000 E to the 0.0175 times 10. And then I would just be able to plug this straight into my calculator and run matrix, which would give me $5,956.23. All right. Question 2 wants to know when you will have $7,000 in the account. So $7,000 is a Y value. So 7,000 is equal to 5,000 E to the 0.0175x, because we don't know that. We don't know what the time is. So again, I'm going to go ahead and graph this function, and then I'm going to do xcal and plug in 7,000 for my y. So let's go ahead and plug this in. Okay, there's my graph. 5,000 e to the 0.0175x. Okay, I'm going to do gsolve. I'm going to do xcal because I'm trying to find an x. The y value that I know is 7,000. So after 19.23 years, okay, I will have $7,000 in the account. All right, so after this, guys, we're going to start transitioning into logs, but we will come back and look at these graphs, especially when we look at exponential and log graphs together.